Hello and welcome to Textbook Engineering Problem. Today we're looking at Elementary Principles of Chemical Processes, 3rd edition. We're doing problem number 2.36. I'll read the problem statement. The relationship between the pressure, P, and volume, V, of the air in a cylinder during the upstroke of a piston in an air compressor can be expressed as PV to the K equals C, where K and C are constants. During a compression test, the following data are taken. Okay, so then it gives us a table of values. Determine the values of K and C that best fit the data. Give both numerical values and units. 2.36. We've got PV to the K equals C. Okay, let's turn this into a linear equation, so we can do linear regression on it and then solve for the parameters K and C. Okay, so since K is an exponent, I think what we're going to do is move V over to the other side, and then we can take the natural log and get this expression. Great. Okay, so that looks a lot like a line where y equals the natural log of p, x equals the natural log of v, m equals minus k, and b equals the natural log of c. And our model is a linear model. Okay, so now we have to do linear regression on this model and determine what the constants m and b are. And then from that we can determine what k and c are. So let's move over to the computer. Okay, so we've moved over to the computer here, and I'll start programming our equation. So we have P and V, and then we have Y and X. I'll go ahead and plug in the table values. Okay, and then we'll convert these into our Y and X. Okay, now we need our parameters M and B. Okay, I wanted to do something a little different in this one. Normally I use the computer to do the linear regression, but there is an equation in the back of the book that we could use, and that's what they tell you to use as part of this problem. So if you look in the back of the book, they've got this Appendix A.1, which is the method of least squares. So for a linear least square regression, the slope and the intercept are actually defined and can be solved. They have their like a mathematical formula that they can follow based off of the data that you have. And so we could use that formula to solve this. It's a lot easier for, like, a lot of these functions are already programmed into Excel. So there's already a function called slope, which returns what this function is. So slope and intercept are those functions that they give to you in the back of the Elementary Principles of Chemical Processes 3rd edition book. Appendix A, they give you the handwritten formulas. So you could go through and hand calculate what the slope and the intercept are You don't have to solve it numerically or by guessing and checking, like I've done on some of my previous episodes. And so I did just want to point that out. But if your model is not linear, like how we've been doing it in all of these cases, where we've been using a line to model our problem, if you wanted to instead use a nonlinear model or have more than two variables, then usually you would solve that numerically. But this is a pretty good method of solving a system with where you only have two parameters and you can fit it to a linear model. Yeah, I just wanted to make you guys aware of that. This setup does exist. Anyway, so that's our slope and our intercept. From our slope and our intercept, we can determine what the value of K and C are. So M is the opposite of K. So minus M. So that's what K is. And C is the exponent of B. So those are the values for K and C. Now we need to do a little bit of unit conversion here because we need to examine our function and see what the units are, because the pressure that we were given is in millimeters of mercury and the volume we were given is centimeters cubed, and they asked for the values of K and C and their units. So let's move on from here. P is in millimeters mercury, and V is in centimeters cubed. If our function looks like this, P equals V to the minus K times C, then that means that this term needs to have units of millimeters of mercury. Okay. That means that, here, let's set it up, millimeters of mercury. And we know that volume has centimeters cubed, and it's raised to the K power. That means that K is unitless because K is an exponent in this case, and exponents cannot have units. So that means that C, which is units, we don't know what they are. We can calculate what the units of C are by just solving for it algebraically, as you see in this equation that we've set up. So the units of C equals millimeters of mercury over centimeters to the negative 3K power. a little odd units, but you get weird units when you're doing empirical relationships. Okay, so we have solved the problem. Okay, so that's it for 2.36. Thanks for joining me. If you have any questions about this, put them in the comments. Questions, if you saw any errors that I made, I'll post corrections if you guys have any suggestions. I'll review those. If you need help on another problem from this book or from another book that I have access to, feel free to leave a comment as well, and I'll try and read those and address those problems. I've got a pretty large background in engineering and science, so I could potentially help if I'm familiar with the context. So just let me know, and I will take a look at that. Thanks for watching the video, and I will see you in the next video, hopefully. Thanks. Bye.